How we doing? We all good?
Well,
Good to try this sunny Colorado summer. All right.
Yeah. Like yesterday was slightly warmer.
So today we're going to again start off with a lecture. And it's going to be, yesterday was by far the longest lecture that I'm going to give you. It was just kind of the introductory, so that we had to cover a lot of ground. Today will be a much shorter endeavor. So we're going to talk about lasers. So the flavor of this is going to be quite different than what we're going to talk about in the next few days or what we talked about yesterday. Like I said, this is the point in the discussion where we actually have to talk about quantum mechanics a little bit. But to frame the discussion for lasers, I think it's interesting. Lasers are a very special kind of light, obviously, and they have some very special properties that allow them to be very useful. And but in order to really appreciate lasers and their qualities and what's so useful about them, it's a good thing to start off by surveying other forms of light. And one of the ways I like to frame the discussion of other forms of light is to kind of talk about, since this is after all field session, you're supposed to be coming at this material with sort of a design mentality, learning things and then trying to figure out how to use them to build or design things. I like to frame this discussion in the context of creating more efficient light sources. So, kind of track the history of developing really efficient light sources. So. Our discussion today is going to start, before we actually get to lasers, with just a generic discourse on the emission of light. So let's talk about some of the broader categories of light emission, what they entail, and what they can be used for. How efficient they are. So before I get into this discussion, part of our analysis throughout today is going to be hinged on different energies of light. And one thing we know is that quantum mechanically there is an energy per photon which is proportional to the frequency, h bar nu. Okay? So the energy per photon scales as the wavelength of the light that you're dealing with. And so it's useful to remember that if we think about the spectrum as, say, increasing in lambda, then we have the visible part of the spectrum sort of in the middle between 400 and 700 nanometers. That's a 4, not a 9. And if we go to larger wavelengths, all right, by the way, what color roughly is the 400 nanometer?
Red.
Purple.
It's either blue or red.
Blue.
Well, it's either red or violet. But which one is it? Red or is it violet?
Violet.
Who says red? I love this game. Who says violet? I don't even remember which end I was talking about. 400? Yeah, the 400 is violet. Yeah. Okay, I'll call it violet. And this is red. Okay. And if we move beyond the visible and we go off, for example, to larger wavelengths, then we hit what is naturally called the infrared part of the electromagnetic spectrum. And if we go off into the sub 400 nanometer wavelength part of the spectrum, then we're in what's called the UV, the ultraviolet. Okay? Maybe I should really stick with my Chuck Stone style color designations. Even write red, violet, and red, and violet. Okay, so that's wavelength, but truthfully, we're going to talk a lot in terms of energy, and so it's actually more appropriate to talk about how these things scale with energy. And remember, energy per photon is h bar omega, or h nu. But for light traveling in a vacuum, we know that the wavelength and the frequency are related by that expression. So as the wavelength gets bigger, the frequency gets smaller, and vice versa. So in terms of scaling with frequency or energy, they're interchangeable because they're proportional to each other by a constant, then we should think of the ultraviolet as energy scales where the photons on average have more energy than visible light, and infrared as scales where the energy per photon is lower than visible light. And you, of course, are probably familiar with this. The ultraviolet light from the sun is the one that actually damages your skin. Infrared light sounds scary, but it's not. You can't see it, but it's not really damaging. Unless it happens to be coherent and you get a long exposure in your eye or something like that. But generally speaking, we don't worry too much about infrared. Visible light is obviously our friend, and ultraviolet is where all the nastiness arises. Okay? Again, this is the energy per photon. The total amount of energy you have is, of course, this energy times the number of photons. So one UV photon is not necessarily a bad thing. Okay, or one ultra UV photon is not necessarily a bad thing. But a very large flux of UV photons, i.e. that coming from the sun, is bad for business. So wear your sunscreen or your hat or whatever. Okay, so with that in mind, let's now talk about some various forms of light emission. And I'm going to start with a discussion of what we call incandescence. And this is sort of the lowest tech way of creating light. You know, cavemen can do this. This is not rocket science. Incandescence is what I like to call hot light. That's why I'm using the red marker, because it's hot. And incandescence genuinely stems from just taking an object and heating it up. Now, there's something a little subtle about that, because, for example, if I turn on this light here, you're all familiar with incandescent light sources. That filament has a current running through it. It's heating the hell out of it. It gets hot enough, it glows. Hooray, we get visible light. But then we could ask, are you incandescing?
Of course.
You are?
Well, maybe. I'm not.
Who thinks he's incandescing? Yes? No? I mean, if we heated him up enough, he would glow. He'd be rather uncomfortable, but he'd glow. But the truth is, he is putting out incandescent light. Okay? The kind of light that we're talking about when we talk about incandescence is simply thermal light emission. And a long time ago in a land far away, a guy named Planck actually figured out how to describe or how to derive the thermal emission spectrum from an object at non-zero temperature. And what he found was, if you plot the intensity as a function of frequency and temperature of an object that's at non-zero temperature, then generally you get some curve which has what seems like a continuous distribution of frequencies. Okay? And the trick here is, as we increase the temperature of the source, the peak of this curve shifts to higher and higher frequencies. So now remember, there's a range here. So you have the visible spectrum somewhere, and then you have the ultraviolet and the infrared. So at really low temperatures, you're still going to be putting off light, but your distribution is going to be peaked in, say, the infrared, so the emission is going to be largely invisible. Okay? As you start heating something up, and of course one of the nice places to play around with this is with your oven, right? You have your oven eye off, you don't see any incandescent radiation. You see it because you're seeing reflected light, but that's not the thing giving off light. We're talking about light emission, okay? You start turning your oven eye on for my electric stove here, and once it gets hot enough to start glowing, what's the first color that it begins to glow?
Red.
Red, because it's this distribution is entering the visible part of the spectrum at the red end. Of course, if you keep cranking up the heat, usually you can't do it. But if you keep cranking up the heat, you'll start picking up white light, and then eventually that might actually shift to blue. Okay. So my point is, though, anything at non-zero temperature is putting off this incandescent radiation. It's just not necessarily useful as a source of useful light to us unless it's really hot, like the filament in an incandescent bulb. So sorry, sucker, I'm not going to hang you from the ceiling in my condo and use you as a light source.
Why does it go white light before blue?
Well, white is the total of all of the components of the visible spectrum.
Right, so would it contain blue in it?
It would contain blue, but if you shifted this peak to the ultraviolet, then you would have less of the white light part of the spectrum and more of the blue. Does that make sense? Sort of. I mean, so the question is where is this peak?
Yeah. Okay.
So if this peak is shifted far to the right, then this peak is sitting largely in the UV, which has got a larger component of the intensity and the blue part of the spectrum than the rest of the spectrum.
So the only color we can't see is blue. There's other like ultraviolet light coming out of it.
So you can't see the ultraviolet part. Your eyes are not sensitive to that. Your skin is. But if I give you a multi-chromatic sampling of light, if I gave you 100 billion photons, and all but 6 of them were blue, and the rest of them were green, red, and yellow, and you looked at that, it looked blue, right?
Yeah.
That's what I'm saying. If this frequency distribution, starting to stink over here. If this frequency distribution is peaked in the ultraviolet, then you're getting a larger component of the blue part of the spectrum than, say, the red. Okay.
Yeah.
To get truly white light, you need all frequency components represented equally. That's another way of saying when and how you see white light. But there's a caveat to that we'll talk about a little later. Okay, now, is this an efficient light source? Well, first of all, let's actually see that this is true. This actually is what in fact happens. So I've got this nifty little device over here called a line spectrometer. And when I take the clip off, the end of this is going to be exposed to light. And I got a piece of software here that's actually going to plot for me the intensity of light versus this plot is going to be in terms of wavelength, but we could plot it versus wavelength or frequency. It doesn't matter. We should still see the same distribution because wavelength and frequency are interchangeable. So what I'm going to do is I'm actually going to hold this up to the incandescent light source, and as per our discussion, we should see some kind of distribution of the intensity as a function of wavelength that looks roughly continuous. And if I do that, whoops, lo and behold, I think can you guys see this computer? Can you see that one? You might rotate that one around a bit so the groups can see it. Okay, so everybody see this nice continuous distribution? It's got these few little peaks. We can talk about some of those a little later. But roughly speaking, that's what we would expect from an incandescent light source. Okay, now, these are really easy to make. All you have to do is,
How would you increase the temperature to change the color of an incandescent light bulb if you could? Like, we're talking about how you can shift the intensity curve using a shift in temperature.
So with an incandescent light bulb, you can
Up the voltage.
Yeah, if you up the voltage though, so was your question how would you change the
color of an incandescent
color, right?
Could you,
Yeah, that's
if you
tricky
could?
because so you have to balance. If you run more current through it, you'll increase the overall intensity. But then the question is are you increasing the overall temperature? And this is a question of how fast heat is leaving the object. Because if you have a rapid rate of heat loss, then you can dump a lot of energy into the object. Its temperature doesn't necessarily increase a lot, but it will put out more energy. So you'll get a brighter emission, but you won't necessarily have the temperature of the object increase, changing the spectrum. However, if the object is slow to release the energy and you keep dumping energy into it, the object itself will heat up and its temperature will shift before you see. So it's kind of a balance of those two effects. So when I actually turn the dial up on this, this is able to put off energy so fast that the temperature itself is not changing appreciably. It's rather the total intensity is increasing.
Okay.
So you'd have to use a different material. I don't think you're going to be able to see it with a normal incandescent filament. But naively, that's the thing you do is just heat it up, put
Okay.
more energy into it. And in the case of an electrical circuit, you just put more current through it or increase the voltage. Okay, so these are not particularly, they're simple light sources, but they're not particularly useful. And they're not particularly useful because for a typical incandescent light, if we wanted to actually use this to see, what we would have to do is tune or choose our material and our current, that is design a light bulb, such that the peak of this is sitting right over the visible part of the spectrum. Okay, because the energy you get out, okay, is determined by the energy you put in. So if you're putting energy in and all of your light is in the infrared and you're only getting a little bit in the visible, that's not very efficient because you can't use that infrared light, you can't see it. Okay? So you'd like to get your peak sort of centered in the visible. So that's the best that you can do, but unfortunately you still only get a small percentage of the energy output into visible light. Okay, you've got a lot wasted in infrared, and more problematically, you've got some UV coming in. So incandescent light sources are not particularly efficient, but they're super easy to make. You just heat something up. Okay, so they, for a long time, were our primary sources of light. Now, what is going on in incandescent emission? This is a continuous distribution of frequencies, and here I talked about photons, and photons we know have these little energy relationships proportional to frequency, but we also know from quantum mechanics that photons originate from atomic transitions. Electrons jump between energy levels and they emit photons, or they might jump between energy levels by the absorption of photons. So in quantum mechanics, we would think that light emission should be somehow discrete. Light is only created, in these discrete transitions. So how is it that we're getting this continuous distribution of light? I mean, the world is fundamentally quantum mechanical, right? I mean, classical physics is useful as an approximation, but the truth of the world is that it's quantum mechanical. We are made of atoms. So how am I getting this continuous distribution? Any guesses?
It's not actually continuous, but
Exactly.
it's close enough.
It's not actually continuous. What it is it is a quantum mechanical system where if you drew the energy levels, and if you have a hydrogen atom, you sort of draw a ladder of energy levels like this, and these represent the different energy levels. This is a macroscopic system. It is a lot of atoms or molecules. They have many different degrees of freedom. You can have electronic degrees of freedom where the electrons move between energy levels, the atoms can rotate, they can vibrate. All of those correspond to different energy levels of the system. If you actually drew the ladder of energy states, it would look like this. It would basically be this incredibly dense set of discrete states, with the spacing so small that you couldn't actually discern the difference. So you have electrons jumping between different energy levels, but since you can have a difference in energy level of any size you want, and since you have electrons all over this system, the total output of photons looks like approximately a continuous distribution. Okay? So incandescence, this classical version of incandescence, actually arises from the quantum mechanical picture because of a macroscopic system. You're making use of an incredibly large number of densely spaced states. Now I say that because in contrast to incandescence, we can instead talk about luminescence, which I like to refer to as cold light. Generally speaking, luminescence can come in a variety of forms, but the spirit of luminescence is that you have the same atomic transitions that are controlling the emission of light, but in luminescent light sources, you utilize only a few of those transitions. So for a luminescent light source, we might have, a set of atomic states, but we only utilize transitions between, maybe 3 or 4 of them. That means that the photons that come out from a luminescent source only come out with a discrete set of frequencies. So if we plotted the intensity of a luminescent source versus frequency, what we would expect to find are these sort of spikes at the frequencies associated with the photons jumping between the energy levels of the luminescent source. Okay? Now, I'll talk about some examples of this in a moment, but you can already see that because you are working with a smaller number of energy levels, you have more control over the output of these sources. It's probably conceivable that you could tame the output and constrain it to sit largely within the visible in a way that you can't really do here, because this is always going to be a curve. All right? It's a Gaussian distribution, in fact, and there's really no way to completely encapsulate it in the visible. You're always going to have infrared and ultraviolet tails. But this is by no means a Gaussian distribution. Okay? So by picking the right materials for your luminescent source, you could very well end up getting completely visible emission. And that'd be great, because that means all the energy you're putting into it to turn it on, make it go, you're getting right back out in visible light. Okay? Now, a couple of actual ways of getting luminescence are the following. So we'll look at 2 examples. So the first is something called fluorescence. And fluorescence essentially makes use of the following idea. I'm going to have an atomic system that is sitting, I'm just going to, for simplicity, work with 2 states, so state 1 and state 2. And I might have, state 3, or a 3-state system. So I might have a system of 3 states with an electron sitting in the ground state, the bottom state. And then what I can do is send in a photon that is maybe ultraviolet, that is, it's high energy, you can't see it. But this photon, this ultraviolet photon, is tuned to the energy difference between 1 and 3. Actually, maybe I'll label it this way. So a UV photon tuned to the 1-3 difference. What will happen in this situation is that the electron will excite to level 3 by absorbing that photon. But then if we wait, it can de-excite to level 2 and then subsequently de-excite to level 1. And typically in these processes, the photons that come out are an infrared and a visible photon. So fluorescence typically involves the absorption of an ultraviolet photon and then the subsequent emission of a visible photon and an infrared photon. Of course, if you were lucky enough to pick the right system, maybe you get 2 visible photons out. Okay. Can anybody tell me why it might be better to get an infrared and a visible out than 2 visibles? What would be the advantage of that?
With the 2 visibles being reabsorbed by
everything could be reabsorbed. That's always a possibility.
Does that have a certain energy before it can?
Are you asking me a question? You're supposed to answer my question. Any guesses? Greco?
Photon colors don't mix. Like you can fine tune what frequency of light you want, so you're only working with 1 photon.
That's true. If you got 2 visibles out, they probably wouldn't be the same color, and so if you wanted to get a monochromatic source out, that'd be, you'd have to have at least one of them be invisible infrared. So what about this? If I wanted to get two visible lights out, two visible photons out, how high of energy would this have to have? Yeah, it'd have to be pretty high because basically you're halving the energy. But if all I care about getting out is one visible and one infrared, this can be barely more energetic than a visible photon, because this infrared photon can be very, very low energy. And so that means that the UV part that I'm using to stimulate it doesn't have to be really high energy. And generally speaking, we like to not deal with high energy UV if we can avoid it. Okay? We don't really care too much about this infrared. It's low energy, it's not going to hurt us, it's invisible, and it doesn't take off very much of the energy, right? So it's not like we're losing a lot of energy in the emission of these infrareds. Okay. So this is fluorescence, and fluorescence has got its uses. One use of fluorescence is if you want to do imaging in medical imaging, you can actually inject a dye into, say, a tissue sample. Okay, so normally we think of microscopy as we stick something in a slide and we stick it under the objective of our microscope. We look through the eyepiece and we see, whatever the sample is. But that really relies on light reflected off the surface of the sample. That's the light we're seeing. Sometimes we don't really care about seeing the surface of a sample. We actually would prefer to see in the interior. Okay, but that's a problem because when you shine light on something, it reflects off the surface. You don't see what's inside. But you can get around this by actually injecting the sample with a dye that fluoresces. And then you turn off the lights and you illuminate your sample with ultraviolet photons. Those ultraviolet photons you don't see, but when they hit the dye, they cause the dye to fluoresce, to glow. And so you can actually sit and look through the microscope and see the interior of your sample. I mean, you can't see very deep, but you can see the interior. You can see the fluorescence emission that actually makes it back out through the surface. Okay, there's a problem with that, though. Can anybody identify the problem of using this kind of fluorescence imaging in biological systems?
Ultraviolet destroys tissue.
Exactly. If you're throwing in ultraviolet light, your sample, if it's alive, isn't going to last very long. And biology on dead things is not a very interesting subject. So, can anybody guess how you could get around this? So does everyone understand the problem? To get the thing to fluoresce, you have to send in ultraviolet light. But ultraviolet light damages biological systems, especially if you're talking about a few cells in a petri dish. Okay, so how might you get around it? Any guesses?
Two photons.
Exactly. You can actually make use of a phenomenon called two-photon absorption, where you send in two low-energy photons that are simultaneously absorbed. These can be two infrared photons, whose total energy is visible. But because the two infrared photons are invisible to us, they don't contaminate the light output, they don't damage the tissue, and moreover, you're only going to get absorption where you cross the beams, because you have to absorb two photons at once. So two-photon and multi-photon microscopy is actually a relatively recent development in biological imaging. And it's something that I think somebody, is it Jeff, works on? Does Chip do it?
Nope.
Or just Jeff? Jeff. So Jeff Squire in this department is sort of an expert in the technology of multi-photon imaging. Okay, so our second example of luminescence is gas discharge. So in a gas discharge scenario, what we have in mind is we have a cathode and an anode, and these things are plugged into some voltage source. So plug that bad boy into the wall, and then sitting around this is some tube with an ionized gas in it. You get the voltage between the cathode and the anode high enough, you'll induce an electrical current to flow between them. If you've got an ionized gas in there, then you've got charged atoms, ions in the gas. You've got charged electrons flowing through that gas, you can have electromagnetic interactions. And what's important about this is if you pick your ions, if you pick what atoms are going to be in this thing, then you know the electronic structure. If you control the voltage, then you can control the energy of these electrons, and so you can actually fine-tune the kinds of electromagnetic interactions that are going to happen between the electrons and the ions, which allows you to fine-tune how much excitation the ions are going to have, and then therefore their de-excitation and light emission. And you don't have a ton of control, right? I mean, these are collisions, okay? But you have enough control that you can actually reduce this to a discrete output. So you're basically banging the electrons into the ions through the electromagnetic interaction. When you hit the ion, it's exciting it, and then when it de-excites, it emits light. Okay, but it's going to emit it in a very discrete way. So to give you an example of this, I'm going to turn this guy on. You get your goggles on? You have your goggles on? Okay, that's not a laser, so don't worry about it. Okay, so that is a helium neon discharge tube. It's not a laser. That's a helium neon discharge tube, and the helium neon discharge tube is, will you turn the lights off, please? Is just a gas discharge tube. So the ionized gas in there is helium neon, and it's basically applied, we have a voltage source applied across it, we have current flowing, and if I hold this guy up, we'll notice a characteristic, oh my gosh, I'm not getting any intensity. Oh, there we go. A characteristically discrete output, okay? Definitely not continuous. Sorry, I can't aim my pointer. Everybody see that? So there's a lot of spikes in there. We have quite a few transitions that are playing a part, but it is definitely discrete, okay? It's not mimicking a continuous output in any way, shape, or form, and now I can't tell if are you seeing anything?
Yep.
You are? Okay, sorry. All right. You can turn the lights back on. Thank you. So we've got gas discharge tubes, we've got fluorescence, and these are both examples of luminescence, and there are other examples out there. And generally speaking, luminescent phenomena allow us greater control over the light emission, which means that we can produce more efficient light sources. So to give you an idea of the efficiencies, well, let's first of all actually ask the following question. We have evolved, we started off cavemen lit fires, and that's how they, well, actually they just lived during the day, and then when they got smart enough to make fires, they made fires and they could see by night. And then we eventually started, burning other things. And now, what do we use as our primary light source?
Fluorescent?
Yeah, we use these overhead compact fluorescent lights. So what kind of technology do you think those employ?
Yes. Both of those?
Say it again?
Both of those?
Yeah, it actually employs both of these, all right? Which, might seem like overkill. Why do you have to use both of them? But remember, we're trying to design the ultimate in efficiency of light source. So in an overhead compact fluorescent lamp, what we actually have is a thin tube of something like mercury vapor, and it is connected to a cathode and an anode. So we have a gas discharge tube, and when we turn the overhead lamp on, this thing will start emitting light, but that light is going to be in the form of ultraviolet photons, okay, high energy photons. However, that very thin gas discharge tube is surrounded by the larger tube, which is the thing you actually see, which has a phosphor coating on its interior. And the role of that phosphor coating is that when it gets bombarded by the ultraviolet photons coming out of the gas discharge tube, the phosphor coating then fluoresces. That is, it absorbs the ultraviolet photons and then re-emits into visible. Okay. So then we have visible light coming out. Okay. Seems convoluted. You're making use of both of these, but the truth is this is the result of trying to find the most efficient light source you could come up with. So, just to give you an idea of the efficiency that's achieved, if you go back to the Babylonian era, they burned oil from various sources for light. And I got this from a very interesting interview I heard on NPR. In the Babylonian era, if you worked a day, and you took all of the money you made in a day and you bought light with it, you could buy yourself 10 minutes of light in the evening. That's like basically like desk lamp type light. So if you wanted to read a book at night, you could read for 10 minutes, spending all of the money you made in a day. And it was largely that way until about the 1800s. And then in the 1800s, with the development of kerosene as a source, still using incandescent emission, we greatly bumped up our efficiency such that with kerosene as a source, a day's wages could buy you 10 hours of light. If you think about it, spending an entire day's wages to run a lamp for 10 hours is pretty inefficient. Fortunately, you don't live in the 1800s, you live now, and you get to use compact overhead fluorescent lights. Any guesses as to how many hours you can buy with a day's wage with a modern compact fluorescent light? Any guesses?
More than 10.
More than 10, I would hope. Otherwise, I wouldn't say we've gotten very far.
100?
20,000 hours.
Yeah, we go.
Okay. So you should appreciate when I say that people have worked to make these things very efficient. Okay. That, you know, it might seem like a convoluted system, but we don't even think about turning on a light anymore. You know, 200 years ago, you're like, well, I worked today, I get to read tonight, you know, but I better choose a short story because I only got 10. All right, well, 10 minutes if you're in the Babylonian era. I guess they could read anyway, so it doesn't matter. Yes.
Where do you think we'll go next to get
Mars.
even more
Mars.
efficiently?
Mars.
So, LEDs.
Yeah, those are really efficient.
Yeah.
They have LEDs that end up, what was it? They could use like the heat in the room, so they're like, but it bumps the quantum efficiency up above 100%. So it doesn't break physics, but it still does that.
Wow. Yeah. I mean, LEDs are the. I mean, so we as humans are funny people because what we do is we make improvements to make things more efficient, and then we just use more of them. We make everything brighter. We're kind of done that way. We become more wasteful and excuse it because technology allows us to make things more efficient. But you know, the way I would like the world to go is that we would just be more conservative and efficient in our use of things. But you know, and there are limits, right? You have limits on. If you had a 100% efficient light source, then the amount of power that you put in is the amount of power that you got out. And so that sets an absolute cap on what you could possibly do. So what you want to use your light to do, okay, if you want to read, you've got to have sufficient intensity that you're being able to read without straining or whatever. If you had a 100% efficient light source, then there's a minimum amount of energy. We're never going to be able to achieve 100% efficiency, okay, but we're just slowly asymptoting towards it. And LEDs are getting us ever closer. Okay. All right. So now the question though is, we've got these compact overhead fluorescent lamps. They are right now, you know, among our most efficient light sources. They're certainly the things we see most commonly used. So the question is, when I point the line spectrometer at the overhead light, what am I going to see? What color is that?
White.
So you can see something of everything.
Something of everything. I should see the Batman symbol.
As far as wavelengths are concerned.
What should I see? Any takers?
Peaks.
Say it again.
Smooth with peaks.
Smooth with peaks.
I'm going to guess it's not what we're expecting.
Smooth with peaks. That's what we saw with the incandescent, right? Smooth with peaks.
More peaks.
All right, let's do it. Let's do it.
Do it.
Whoa. What are you seeing? Say it again.
It's kind of all over the place.
It's kind of all over the place, but
You have 3 big guys.
3 big guys. We have 3 big guys.
Sounds like red, blue, and green.
Well, if you think about it, if we wanted to create true white light, we would have to use incandescence, right? If we wanted everything, we'd have to use basically incandescence. But we've already said that that's not efficient. However, we don't really want to create true white light. We just want to fool your eye into thinking you're seeing white light. So it turns out if I take an admixture of red, yellow, and blue, your eye can't discern that from white light. So again, it's a question of efficiency. Do we really need to create white light? No, we just want our eye to think it's seeing white light. And we can do that with a discrete output. And that discrete output is key to making these things incredibly efficient. Okay? All right. So that is our sort of story of light emission. And at absolutely no point in any of that did I say a damn thing about lasers. So let's talk about lasers.
Yes.
Yes, lasers. Okay, so laser light. What is laser light? What's so special about it? Why is it different from all these things? Who cares? Just go watch Real Genius and you'll know everything you need to know. Laser. Yeah. Okay. No, truthfully, I think at the end of this, at the end of today, you should go watch Real Genius because you'll appreciate it a lot more you did before this lecture. Okay, so lasers. Oh, he's gonna write that wrong. Laser. No, I'm not gonna do that. Okay, well, people misspell words intentionally. That's what I do.
Lasers and dolphins. Or a shark.
Shark
or a
laser.
Freaking
shark with a freaking laser.
You have to do it, man. It's lasers.
I think every creature deserves a warm meal.
So sharks with frickin' laser beams on their heads. Okay, so what is it about lasers that are so special? So I'll give you 3 properties of lasers that make them distinct from other forms of light, and then we're going to talk about the mechanisms that achieve these properties. So first of all, lasers are, let's see, that word, unidirectional. Another way to say it is they're beamlike. That is, if I take the output of a laser, the photons that come out of a laser are actually moving very, very close to parallel trajectories. Okay? If you think about other light sources, that is not the case. If I turn on this incandescent light, it's shooting out photons in all directions. They're not traveling parallel to each other. If I turn on the overhead light, the photons are coming out in all different directions. They're not parallel to each other. Okay? But lasers output have photons coming out that are very, very, very close to parallel to each other. Now, why is that important?
higher intensity.
They can be focused to a point. Exactly. Remember, if we have a lens and we send in parallel light rays, where do they go? To the focal point of the lens. Now, we talked about this scenario in the paraxial limit. We said if you take the lens very, very far away from a light source, then the light coming from that source into the lens is pretty much parallel. But that's very low intensity, right? If you get very far away from something, you're only getting a small amount of light. The trick with lasers is you can get a very collimated beam of light with a high intensity and then focus it to a point. So you get to take all of the intensity incident on the surface of the lens and concentrate it at a point. Remember, you can't do that if your light is not collimated, because if your light is, for example, diverging or something, or coming in at all different angles, then the lens does different things with it, and it doesn't concentrate it at a point. Okay? So this is the secret source of getting really high intensities out of lasers. We use their collimation and a lens to focus them to a point. So a lot of times the laser beam itself is not so damaging, but after you put it through a lens and focus it, you can actually get some intense results. There's a tour at REO Optics, one of the options for you guys, and I was on that tour a couple years ago, and we walked by this room with toys that they were developing, and the guy said, you know, this thing over here on this table, it was in a clean room. He said, this is an interesting thing because it's a can of nothing. We're like, what? And they had created this little cylinder with perfect windows on each end, and inside of it was a vacuum. And the reason that they had developed this was a guy had asked them to create something because he had a laser that was so intense that if he passed it through a lens and focused it, it would ionize air. So he wanted a way to focus it without ionizing air. So he would stick this can of nothing at the focal point, and that way when the laser actually focused, there was no air there for it to ionize. Yeah, it's pretty intense, and I think Greco said that they have some lasers here that can ionize air. So don't piss Greco off today. Okay, no, just kidding. So the unidirectionality of lasers is a very important feature, and again, it's usually in conjunction with the lens and focusing it to the point where that really becomes useful. Another feature of lasers that is really useful is their coherence. That is, if I take two photons coming out of a laser, they generally have their phases aligning. And the coherence of laser sources is a very useful property when you want to do interferometry, okay, when you actually want to control the interference of light sources. And we'll talk a lot more about interferometry on the fourth day. The third feature of laser light, which is incredibly useful, is that it's a highly monochromatic light source. Okay, it's got approximately one wavelength. It's not actually one wavelength. If I plotted the intensity as a function of wavelength, it would actually be a very sharp Gaussian around that wavelength. So there's always a spread. You can never get a single wavelength. That's sort of an idealized situation. But lasers give us the narrowest distribution around the single frequency that we can get from any light source. Okay. So these are the sort of important features of laser light, which distinguishes them from other sources of light. And you'll notice all the other sources I showed you they were multichromatic. Even the discrete ones had several frequencies in the output. None of them are beam-like, all right? And in fact, in a discussion we'll have in a couple of days, none of them were particularly coherent, right? So how do we actually achieve this with laser light? Well, to do this with laser light, it helps to contrast the underlying quantum mechanical process of laser light with the underlying quantum mechanical process of all of these other forms of light emission. So all of the other forms of light emission have made use of basically a single phenomenon, and that is the following. We have, maybe a two-state system with an electron sitting in the lower energy state. We send in a photon. This thing gets excited, and then it de-excites, and in that de-excitation, we get a photon out. Now, this is so simple that the photon that goes in is the photon that comes out, and we know if you add a third level, you can change the relative frequencies of the photons. But the point of this picture is that we stimulate the system, and then we wait, and this will spontaneously decay and emit light. So this is a process called spontaneous emission. Spontaneous emission is the fundamental quantum mechanical process that underlies all of the light sources we talked about so far, incandescence and all forms of luminescence. Okay? For lasers, we make use of a scenario which looks similar, but it's actually different in a very important way. We start with an excited electron. And to this system, we again input a photon with the energy difference between levels 1 and 2. And what happens is this incident photon stimulates the electron, causing it to decay. But of course, when that electron decays, it emits a second photon. And so our incident photon is sort of doubled. This is what we call stimulated emission. The word stimulated just meaning that you're using one photon to sort of induce the electron to jump down. What's important about stimulated emission is what these two photons have in common. Okay? These two photons share the following properties. They move in the same direction. They are in phase. And they have the same energy. That's not obvious. I mean, I'm drawing pictures. I'm not doing like a lot of hardcore quantum electrodynamic calculations. You can do it if you want. All right, but a careful analysis of this process of stimulated emission will show you that these two photons coming out share these three properties. Now, why are these three properties nice?
Because those are the three laser properties?
These actually correspond to the three properties of lasers. The two photons are moving in the same direction. Well, if I keep compounding this stimulated emission effect and I keep doubling the number of photons until I get a decent amount, then I've got a beam of photons moving in the same direction. They're all in phase, which means that they're coherent, and they all have the same energy, which means they have the same frequency, which means it's monochromatic. So it is this process of stimulated emission that actually is responsible fundamentally for all of these nice properties of laser light. Now, the process of stimulated emission was discovered and worked out by Einstein in the early part of the 20th century. When did we have our first operational lasers?
60s?
Yeah, 50 years later. So Einstein figures this out. Having light sources with these properties, people knew that'd be useful. There was no question about that. I mean, people knew about light. They just didn't know how to make it. Einstein gives us this idea. Why did it take 50 years to make lasers? That's what the rest of this lecture is about. Why is it hard to make a laser? I'm going to teach you why it's hard to make a laser, and then I'm going to let you do it. Okay? So why is it hard to make lasers?
That would be like mad science.
So, to understand why it's hard to make lasers, we're going to have to study the real scenario of creating a laser, because there are a series of obstacles that you have to overcome in creating a laser. First of all, the process of stimulated emission can take one photon and turn it into two photons, but two photons does not a laser make. Two-photon laser is not a very powerful laser. We would like a large output to our laser. So the obstacle of creating a laser is to get a significant output. Okay, two identical photons isn't very interesting. Okay, it's like identical twins is not interesting, but if the entire world were identical people, that would be weird. That'd be like a laser. Okay, so all right. So let's think for a moment about how a laser works. So we have some material that sits in some cavity. And this material, it just depends on the type of laser you're dealing with. It could be a liquid, it could be a gas, it could be a solid. But generally we call this the lasing medium. Okay. In class today, you're going to use a gas discharge tube. So your lasing medium will be the helium neon gas in the gas discharge tubes. But you can certainly have liquid lasers and solid lasers. So generically, there's going to be some stuff inside of a cavity. And what I would like to talk about is what happens as the power at one end of the cavity moves along the cavity. So what I mean by this is, we want to use this stimulated emission to kind of multiply our photons. And as we multiply our photons, we're increasing the power. Okay, that's what we'd like to do. So we'd like to quantify how much of this is actually happening across a laser cavity. Okay? So let's actually draw sort of a side view of this. So we have our z-axis, and at z equals 0, we have some initial power P naught, and the question is, what power are we getting maybe coming out this end? And it turns out that the power as a function of z, well, actually the rate of change of the power as a function of z is proportional to the power at the location z. And just by convention, I'm going to write this proportionality as minus alpha p of z. Okay. So this is a lot like a populational equation, right? The greater your population, the more your population is typically increasing. Okay. So the rate of change is proportional to the amount that's there. So this is a fairly generic situation in nature and in physics. You can argue more technically that this should be the case, but I think that this is probably a reasonably comfortable conclusion. Now the question is, what is this alpha? Well, before we even know alpha, we can solve this differential equation, and we find that P of z is P naught times an exponential function of z. And then the key is, what is this alpha? Well, alpha is called the absorption coefficient. And the important thing about alpha is that it is proportional if we take a two-state system, and in my lasing medium I have N2 electrons in level 2 and N1 electrons in level 1, the absorption coefficient is proportional to the relative populations of level 2 and level 1, N2 minus N1. Okay? Where this proportionality constant is positive. Okay, it doesn't matter its absolute numerical value, only that it is positive. Sorry, I got this backwards. This is N1 minus N2. My apologies, and I have to get that right. Okay, so let's, just to keep this simple, we'll look at a two-state system, so we only have, transitions between 1 and 2 to worry about. I'm going to start out with N1 electrons in state 1, N2 electrons in state 2. And then if I send in power at one end, the amount of power I get at the other end is governed by this equation, where z is, you can take this to the length of the cavity. And the behavior seems to be controlled by this absorption coefficient alpha. Now let's look at a couple of examples of alpha. So if N1 is greater than N2, what's the sign of alpha?
Positive.
Yeah, if N1 is greater than N2, then alpha is positive. And what happens to our power as it moves through the cavity? It decreases. This is what we call a lossy medium. It absorbs the energy that's trying to move through it. That's not what we want. Boo. Boo on lossy. Ew, linear test. Okay, so we don't like lossy media. Unfortunately, this is the situation that we usually start with in nature. If we just went out and we just found a two-state system like laying on the ground, you'd have more electrons in the lower energy level than the high one. Okay? This, unfortunately, is the usual configuration. Okay? We are not going to just walk out and find something that's not in this configuration. Okay? However, if we could somehow achieve the scenario where N1 was less than N2, then what would be the sign of alpha? It'd be negative. And what would happen to the power as it moved across the cavity? It would increase. So we would be, this would be a gainful medium, or we would have gain in our laser cavity. So to get gain, we need a larger population in the excited state than in the unexcited state. But again, that is not the natural way we tend to find things. So to distinguish this as an unusual circumstance, we refer to this scenario as population inversion. Okay, that is the relative populations of these two states is not what you typically find. It's like if the world were full of rich people and there was only a couple of poor people. That would be population inversion. You guys are supposed to laugh at my jokes. And you're supposed to laugh at them whether they're funny or not. Don't laugh at the bad ones. That's just, yeah, anyway. Okay, so, So to get gain, to get this effect to actually give us a greater output than what goes in, all we have to do is achieve population inversion. Well, that's fine. What do? We go out in nature, we just pick up a system. It's going to be like this, but how do we make it, how do we invert the population? What do we do?
Excite the electrons.
How? We just,
More photons.
how about we, take the whole thing, plug it into the wall. Put energy in, right? If you start out with, fewer electrons in the excited state and more of them in the unexcited state, and you just start dumping energy in, what are you going to do? You're going to excite the electrons, right? So once you've excited enough electrons, you'll have population inversion, and then, now, do we have to start this cascade of stimulated emission, by the way? Do we actually have to do anything to start this? Why?
Spontaneous emission.
Yes, somewhere in this cavity there's going to be a spontaneous emission. But that spontaneous emission can then act as the seed for the cascade of stimulated emission. So all we do is plug this thing into the wall, we dump energy in, we excite it, we get a population inversion, and then some spontaneous event will induce a stimulated cascade, and we'll get a laser with gain. It'll be awesome. Okay? But there's a problem. Does anybody see the problem? Well, we could keep dumping energy in, right? We could dump energy in at a rate such that as these jump down, they immediately jump back up. So we would have to keep putting energy in to sustain that population inversion. And if we turned it off, you're right, it would eventually cascade back down, but there's a bigger problem.
Is it that we can't tell immediately where the spontaneous emission is going to send a photon, so we can't control which direction it goes in? Or?
Well, that's actually an issue that will be addressed in a slightly different way, but we will talk about that in just a moment. But at this level, there's a bigger issue. There's one more combination of N1 and N2 that I have failed to address.
Equal.
That's when they're equal. What is alpha when N1 is equal to N2? Zero. What happens to the power when alpha is equal to 0? If alpha is 0 and you put energy into this laser cavity, it's basically transparent to that energy. It cannot absorb anymore. The energy just passes straight through. Alpha equals 0 is a roadblock. But it's a roadblock you have to pass through if you want to go from here to here. You can't go from a negative number to a positive number without going through 0. This would be okay if we could find materials which were already population inverted, but none exist. They always start out like this, and we have to get them here. So how are we going to get through that alpha equals 0 roadblock?
Add more electrons.
I liked the first two words of your answer, but I didn't like the third.
Have more energy levels.
Add more energy levels, okay? If we actually allow ourselves to go beyond 2 levels, we can circumvent the alpha equals 0 roadblock in a very interesting way. So let's, instead of a 2-state system, consider the following. Let's take a system of 3 states, 1, 2, and 3. And for this 3-state system, we're going to have a series of transition rates. So I can have the rate, so that's a capital gamma, and that's just the probability per unit time of an electron transitioning between levels 1 and 3. If the rate between 1 and 3 and the rate between 3 and 2 is much larger than the rate between 2 and 1, then we can ask ourselves, what happens if I start out with a bunch of electrons in the first energy level and I start dumping energy in?
I'm gonna get the heck out of there.
Say again?
They're gonna leave.
I'd be excited to.
Get rid
So,
of it.
so before I actually talk about the 3-state system, let me go back to this 2-state system for a moment and talk about the alpha equals 0 roadblock in a slightly different language. If I have a 2-state system, then the only rates I have are gamma 2,1 and gamma 1,2. That's the rate down compared to the rate up. Those 2 rates are always the same. Okay? That is, if I have an electron sitting in level 2 and I have an electron sitting in level 1, the probability per unit time of each of them making the transition to the other energy level is the same. Now that does not mean that I have the same number of electrons jumping up that I have the same number of electrons jumping down, unless I have initially the same number of electrons here that I have here. If I have the same number here that I have here, and the rates are the same per electron, then I'll have the same number going up that I have going down, and you don't get any population inversion because you're just stuck at equality. If I start with all of them in level 1, even though the rates are the same, there's no electrons to transition down. So I'll definitely have a net transition rate going up. Okay? In this 3-state scenario, though, you can now imagine what happens as you start dumping in energy. You get very quick transitions from level 1 to 3. So remember, these are all equal to the corresponding transition rate in the other direction. So you get very quick transitions from 1 to 3, and you get relatively slow transitions from 1 to 2. So you don't have very much going to 2 in any given unit of time compared to transitions from 1 to 3. But then once you start getting things in level 3, you get quick transitions back down to level 2. Okay? So these are quick as well. But once you get electrons in level 2, they very slowly transition back down to level 1. So what we've achieved in this 3-state system is we've basically given the electrons a fast route to get to level 2, but they only have a slow route to get back to level 1. That's something that we could not do in a simple 2-state system because you've only got the rate up and the rate down, and they're intrinsically equal to work with, right? So we take this medium, this 3-state system, as we find it typically with everything in the ground state, or a lot more in the ground state than anything else. We start dumping energy in, we wait a little while, we'll get more electrons in level 2 than in level 1, and then this transition, after enough time, will provide us with the population inversion we need. We will have more in level 2 than in level 1. Right now.
Waiting.
Exactly. You have to wait. You have to wait for enough of the electrons in state 1 to get to state 2 so that you actually have population inversion. You'll get there, but you have to wait. When's the last time you waited on a laser? You got the laser pointer, you push the button, 5 minutes later it comes on. That does not happen. That is not a good laser. Okay. How can we eliminate the wait time? Any guesses?
Excite the particles.
Excite the particles more, faster, gooder?
Better.
More particles?
You could go and explore materials where maybe these transitions happen more rapidly. But there's a more efficient route to get to it, and you said 2 words, and I like the first one, but not the second one. Not more particles, but
More photons?
more. Say it again.
Energy.
More energy
Levels.
levels. Yes. If 3 is better than 2, guess what's better than 3? 4.
Why not 100?
Well, it turns we're not going any higher than 4. Don't worry. The game stops here. It turns out that if we take 4 states, then we get an even better laser. If I have 4 states and then I have the following relationships between the transition rates, and we're not going to worry too much about analyzing this very closely, but there's a lot of transition rates here, so I have to list them all. Gamma 1, 4, gamma 4, 3, gamma 2, 1 is much larger than gamma 3, 2, which itself is much larger than gamma 3, 1 and gamma 4, 2. Then what happens is, if I start out with a bunch of electrons in level 1, and I start dumping energy in, I get, and I'll draw it in red because red is fast. Red is the color of fast. Flash is red. I get rapid transitions to level 4. I get rapid transitions down to 3, but blue is slow. I get slow transitions to level 2, but then once things hit level 2, I again get rapid transitions back down to level 1. So as soon as I turn on my system, I'm going to have electrons move rapidly to 4, rapidly to 3, but they're going to hang out in 3 a while before they go to 2, and then once they get to 2, they'll go right back down to 1. Why does this solve my time delay problem? I still have to wait to get rid of all these, right? To get more in level 2 than I have in level 1, right?
There's more ways to get to level 2.
More energy levels.
I agree with you that there's more. I agree with you, but neither of those answers are exactly what I'm looking for. Don't I still have to wait to build up a bunch of electrons in level 2 compared to level 1 to get population inversion?
Oh, you have level 3?
What about level 3?
Couldn't you just stimulate transition, whatever, from level 3 to 2 or 1?
So say what you said again.
Sorry. Could you use like stimulated transitions from level 3 to level 1 or level 3 to level 2?
So the point is that this is my lasing transition. Not level 2 to level 1. But think about it. If I start out with all the electrons in the ground state and no electrons in level 2, how many electrons do I have to get in level 3 to have population inversion? 1.
Nice.
Okay. So a 4-state laser, you push the button, it comes on. No wait. Okay.
Is that like the normal amount of energy states in lasers, like 4, or do
No. Greco, any idea on that one? What was the question? The number of energy. I asked Greco these questions because he's actually a graduate student in optics. Not a lot of laser physics comes up in string theory, surprisingly. But how many states do your lasers typically?
We'll use 4-state.
4-state? Yeah. But no higher?
No, I don't think there's any reason to go higher.
So are these rates set by the material?
Okay, so that's an interesting question. So how do you go about, finding the materials or deciding what materials to make a laser out of? So the truth is that the rates are determined by the atomic or molecular structure of the thing you're dealing with. You can't control that. Like I can't take hydrogen and change its energy structure, but you can pick different materials. So there's a lot of material science research that goes into exploring the properties of materials, in particular their atomic structure, molecular structure, and the energy level structure, to figure out which materials will make good lasers. So you can engineer them in the sense of combining things, making molecules, and with maybe nice energy level structures, but you really just have what nature's provided you. Okay? But you can't take a given material and change its structure, like you're stuck with what it is. All right? Okay, so now we figured out, a four-state laser is going to give us, this instant population inversion. Population inversion gives us that absorption coefficient that has the right sign, and we're going to get some gain. So let's turn it on. Let's do this. So let's take our laser. Let's take our laser. About that long. Got some helium neon gas in it. Just got this nice 4-level system. All right. We plug it into the wall. We get that population good and inverted. We get some stimulated event over here, or some spontaneous event. Okay. That spontaneous event, which is going to happen somewhere at some point, is going to create a cascade of stimulated events. And just to get sort of the maximum gain, let's say that the spontaneous event happens at this end of the cavity. So, and let's just suppose that it was moving towards the right end. So as it moves across the cavity, it keeps multiplying, and we can ask how much comes out. So if I've got an intensity at this end of I naught, after that intensity moves across this laser cavity, if I see that laser tube, that helium neon tube's about that long, how much intensity do I get out the other end? Any guesses? How much gain do I get? How much gain do you want? You want a lot, a little?
A lot.
All right, so what do you think we're going to get? How much gain do you think we're going to get as the intensity at one end of that gas discharge tube moves across and it has this cascade of stimulated emission multiplying that signal? Take a guess.
14.
10 to the 14? 1,000?
A lot.
A lot? Hell a lot? Hell a lot of gain? You get about 2%. It's not a very impressive laser at all. How are we going to improve this?
Belts and back and forth.
Well, one thing we could do is make the tube longer. If we made it 100 times longer, we could bump that gain up, okay? But that's not a very practical laser. Imagine giving that lecture. Let me get out my 10-meter laser pointer. Okay, no, we're going to use mirrors, okay? So now we are finally approaching the configuration of the modern laser. This is the last obstacle. How do we take a relatively small amount of gain and turn it into something that's really useful? So in a typical laser configuration, we put 2 mirrors on each end of the cavity. One of them is what we call the high reflector mirror, the HR, and it is designed to be 100% reflective for light in the wavelength range of the wavelength you're trying to get a laser output from. It's not the whole wavelength range of the tube emission, but the particular frequency you want to come out in the form of laser light. The second mirror we call the output coupler, or the OC. That's not the TV show, that's the mirror. The output coupler is on the order of 98% efficient. Or sorry, 98% reflective. That means that a photon will, on average, bounce off that mirror 98 times before it leaves. Whereas for this mirror, it'll bounce off typically 100% of the time. That means if I have a photon at one end of the cavity that begins the cascade, it's going to move to this end and then bounce back and forth about 100 times before it eventually leaks out that end. But on each pass, you're getting a 2% gain, so after 100 passes, you've got an appreciable gain. Okay? So all we have to do to make a functioning laser is take some tube, four-state system, plug it in, achieve some population inversion, put two mirrors on each end with the right reflectivities, and out comes the laser. Yeah?
What would happen if you increase the reflectivity of the OC to like 99.9? Would that help?
100.
Well, that's an interesting. Well, 100 would be interesting. So all of these possibilities you're going to get to explore in just a few minutes, because you're actually going to work with a FET simulation that lets you actually play around with exactly that. You're going to have a simulated laser tube, and you're going to try and get it to laze, and you can see what happens when you increase it to 99.999%. Okay. Generally speaking, things get bad in here. Right? So this seems pretty straightforward, right? We put two mirrors on the ends and we let the light bounce back and forth. Let me show you the size of the mirrors we're going to be using. Is that little dot right there? You guys see the dot at the end of that? It's about the size of a pencil eraser. That thing right there, I might not touch it. That's your high reflector. It's about as big around as an eraser. The other mirror has to go out here. Now you're going to take those two mirrors, that small, and you're going to align them so that light can bounce back and forth 100 times between them.
Millimeters count, guys.
That sound easy? That sound pretty straightforward?
Straightforward, yes.
So, I mean, of course, the problem you can all imagine is if your mirrors are even slightly unaligned, if there's even the slightest angle between them, the light is going to walk off. This is what we call walk off. It's not going to bounce back and forth 100 times and stay
It's like Zoolander.
between the two. It's going to walk off the side. So, how in the world are we going to do this? Are we really going to take two mirrors and try and align them perfectly? Do you have any idea how hard that would be? If you don't think it's hard, we can get you set up with the opportunity to try it. No, there's one more piece of technology to bring to this story. Can anybody guess how we're actually going to try and reel in this walk-off? Keep the thing stuck between the two mirrors.
By a laser pointer.
By a laser pointer. Say it again?
A thing like this, a mirror that like focuses it back in.
So don't use flat mirrors, use the curved mirror. Or curved mirrors.
Yeah.
Okay? So you can use two curved mirrors, but I'm going to do an analysis, a very quick analysis, using one curved and one flat. Okay? Because I can actually show you how this works. But generally you could use two curved mirrors. What you don't want to use is two flat mirrors. That's not going to work. Okay? So imagine that we have a flat mirror and then we have a curved mirror where the flat mirror is at a distance r from the curved mirror. Okay, so it's basically the separation between these two is the radius of the curved mirror. If I had a photon in this situation that started maybe at the flat mirror and was moving towards the curved mirror, if it happened to be moving right along the center of the beamline, then it would happily bounce back and forth as many times as it needed to before it leaks out of the system. Okay? But if that photon was even slightly off axis, what happens when it hits the curved mirror? So this is the radius r, and this photon is coming from basically the center of the circle. Where does it go when it bounces off the mirror? Right back towards the center of the circle. So this photon, when it bounces off the mirror, is going to go right back towards the center, but then it bounces off a flat mirror and goes right back. And this guy is just going to go back and forth as many times as he needs to until he leaks out of the output coupler. And in fact, you can capture photons at any angle so long as they don't actually miss the curved mirror in the first place. Okay? There's a second scenario where we can control this, and that's if we put this thing even closer. So if we put the distance between these to be half the radius, so the radius of the circle is here. If I start with a photon here, and it hits the curved mirror, well, if it goes along the center, it's fine, it'll just bounce back and forth. We know that's okay. But if I have a photon which is off axis, and it hits the curved mirror, where's it going to go? So this is not the center of this mirror. This is the center. So I have a photon coming from this point bouncing off of a curved mirror.
It's going to bounce back to where the actual center is.
What is bouncing on the axis?
What is this? That's the focal point. So if you're coming from the focal point bouncing off a mirror, where do you go? Yeah, you go parallel to the axis. So this guy is actually going to bounce off and go parallel to the optical axis. But once he hits the flat mirror, he's just going to bounce right back to the curved mirror and go right back towards the focal point. And then bounce off the flat mirror, bounce off the curved mirror, and happily repeat this pattern until it leaks out the output coupler. Okay. So by using a flat mirror and a curved mirror at either of these two separations, we can sort of control this walk-off. All right. Fortunately, you don't actually have to set it at exactly these distances. These are called the limits of stability. And it turns out that as long as D is less than R over 2 or greater than, or less than R or greater than R over 2, if the distance between the two mirrors is between these two extremes, then you will actually have a stable optical resonator. You'll control the walk-off. Analyzing that's much harder to do than these two simple examples, okay? So when you're putting your laser together, you already have the output coupler bonded to the back of the laser tube. You're not going to have to do anything there. What you're going to spend a large part of your day today doing is putting a mirror right there. Of course, you'll turn this on, but you'll put a mirror right there. You're putting the output coupler in front. The trick is if you put it in there and you get it in the right orientation, you'll get a laser. Of course, if it was as easy as it seemed, I wouldn't dedicate an entire day to it. All right. But one constraint is that you have to make sure your output coupler is placed at least somewhere in this range from the high reflector. Otherwise, you won't get a stable resonator. Yes?
Is there a high reflector, the curved, or the flat mirror?
Well, you could use either. You can use either one. For these, the high reflectors are curved and the output couplers are flat. Yes?
So if we get it correctly, we should see a beam basically coming out of the output coupler?
Exactly. So you're going to put an output coupler mirror in front of this, and generally when you just stick it there, nothing's going to happen. This is just going to look like a glowing tube. But as you align it, if I have a viewing screen here, when you hit the right alignment, you'll see a laser. And it'll be instant. You'll see a laser illuminating the output screen. Okay. So that is, that's all I have to say to you. Are there any further questions? All right. So I'm going to give you a couple of oops, I'm stealing your folder. A couple of words of advice before you get started. First of all, the first thing you're supposed to do is turn on your computer and open up this FET simulation. And that's going to allow you to kind of toy around with the principles underlying lasers. Okay, so you're going to follow those instructions very carefully, because if you don't click the right options in that simulation, there's no way you're going to make a laser. So make sure you read the instructions. As soon as you get the simulation to laze, you can then play around with what happens if you take it to 100% reflectivity. That's always fun. Then you're going to start setting up the alignment of your lasers. Read the instructions completely before you start. Because if you start setting things up and you don't think about where you're putting things, you're going to make your lives miserable. Because I'll tell you this, you're going to have your hands on the output coupler a lot. And if it's in the very center of your table, it's a pain in the butt to reach that. Okay? The output of your laser, once you get it to laze, is something that you are going to use for the rest of this part of field session. So if the output of your laser is pointing at a wall 2 inches from the wall, that's not very useful. So make sure that the output of your laser is going in some place that you'll be able to put things there and utilize it later. Once you've got these lasers aligned, they're bolted down. You're not moving them. You're not going to pick them up and move them. So just think ahead about where you're going to place things before you go ahead and start the alignment procedure. All right, go ahead, log in, open up that FET,
Should we take apart our camera setup?
and
Yes.
Okay.
take away.